Today's lesson will focus on parametric equations. Our objectives for today are that students will be able to define and graph parametric equations. You'll be able to eliminate a parameter and identify the graph of a parametric curve. Students will be able to determine parametric equations of lines and line segments. And last but not least, students will be able to use parametric equations to simulate projectile motion. We looked at an activator in which we discussed a falling rock and how we could have a separate equation for its x position and its y position based on a separate parameter, which we call time. And our instructional focus will delve more into this with regard to what is a parametric, how do we eliminate a parameter, parametric equations of lines, and last but not least, simulating motion. So let's jump in with what is a parametric. All right. The definition of a parametric curve or parametric equations is that the graph of the ordered pairs x, y, where x is a function based on a separate variable t and y is a different function based on a variable t. They're functions defined on an interval of t values. All right, and we call this a parametric curve. The equations are parametric equations for this curve, and the variable t is a parameter, and I is the parameter interval. All right. So we're going to have an interval of time, maybe 1 to 10 seconds, and it doesn't have to be time, but time is one that we tend to use, and it's just where we separate and we define x based on that parameter and y based on the same parameter, and we can model the x and y positions at any point, and we can model a curve or a line or a graph using two separate equations instead of just one based on x and y. You might ask the question, well, what's the point of doing this? Why would we want to have these variables defined on some other parameter? Well, if you say we wanted to model, the amount of items sold at a beach. Somebody's got, on the beach, they are selling soda and suntan lotion, for example, just two totally different things. Now, if they're out there selling soda and suntan lotion, the amount of soda they sell isn't based on the amount of suntan lotion or vice versa. Though it doesn't really make sense to think of one in terms of the other, even though they might, you might be able to graph it as such, where as you sell more of one, you're going to sell more of the other. That might be true, but what really is the parameter defining how much they're selling? Maybe it's temperature. Maybe it's the amount of sunshine. Maybe it's better to define those in terms of something else because it just makes more sense. And so and we might want to graph the comparison of the two with your x and y coordinates, but it wouldn't really make sense to define them in terms of each other. You wouldn't define how much soda you sell in terms of how much lotion. But you might say, hey, I'm going to sell more soda on a hot day than I would on, a cooler day when there are fewer people at the beach, something like that. So the point of, having these parametric equations is because it might make more sense to model your equations, on some other parameter that isn't one that's necessarily being graphed, but it's something that makes more sense in terms of defining your equation. So if you were asked to graph a parametric equation or parametric equations for the given parameter interval, all right, we want to graph this same particular parametric equations, right? We have one for x, one for y, and we want to graph them based on the parameter given. So the first one says from -3 to 1. All right, so if t is -3, then our x would be -3 squared, which is 9, minus 2 is 7. So I'd go to the x value of positive 7. And then I'd say, well, what is my y value at -3? Well, it's going to be -9 because 3 times -3 is -9. So I would have a point here at 7, -9. Notice it's not a point at x is -3, right? T is a separate thing that's not actually on the graph. We're going to determine our x and our y value and then plot the point. If I put in a -2, I would get 4 minus 2 is 2. So I'd now say my x value is 2 and my y value is -6. All right, if I go to 1, my x value would be -1 and my y value would be 3, and it would be up here. And I can go on and on and on. And what about 0, right? It would be -2 and 0, so I'd have a point here. All right, and this might be enough to kind of show you what this is going to look like. If I were to graph it on a calculator, notice we would have that curve. It's kind of a curve like this. I didn't know for sure that that's what it was going to look like, but I would have to graph, other subpoints. But that's essentially what we have here. It's this curve like this. All right, the second one just increases our interval. It goes from -2 to +3. So it's just a different interval, and it's at -2. So this one we're probably only going to see, from that point on in our graph. And if we look at the graphs for each of these, we can see that, interestingly enough, even though our interval changed, it wasn't the interval for x, right? It's the interval for t. So we get different x values depending on the t. And if we go -3 to 3, we get the entire curve. What's pretty interesting about this is, just because the parameter interval changes doesn't mean that, we're going to only go, for example, on the second one I said, we go to -2, it's -3. Well, it doesn't mean we're only going to get this part of the graph, right? We ended up actually getting more of the upper part of the graph, but we wouldn't know that because we're not just plotting x's and y's. The parameter t does not tell us which x values are being used until we apply it to the actual equation. So we plug in the values to get both points, the x point and the y point, and then we plot those particular points. So parametric equations can be really nice in the way they define our functions, but it's pretty difficult to graph them or to really visualize what the graph is going to look like based on the two parameters. Sometimes we can actually eliminate the parameter. We can eliminate that t from the equations and get a function based on just x and y, in which case it's much easier to visualize. All right, so we're going to do an example where we can actually eliminate a parameter. So if I'm given x equals 1 minus 2t and y equals 2 minus t, I should be able to eliminate a parameter. And the way in which I would do this, I would actually solve for t for one of the equations. So I'm going to do it for x. So I have x equals 1 minus 2t. I'm going to subtract 1. I get x minus 1 equals -2t. Divide both sides by -2. So I get negative x minus 1 over 2 is equal to t. All right. When I apply that negative, I actually get 1 minus x over 2 equals t. So now I have a value for t. So now I'm going to go ahead and plug that into the equation for y. Y equals 2 minus 1 minus x over 2. And then the minus, we can apply it again. So that equals 2 plus, it's going to be x minus 1 over 2. All right. And so all of a sudden, I now have an equation. Y equals, and now I'm going to separate this out just so we get it in our slope-intercept form. Y equals x over 2 minus 1/2 plus 2. And -1/2 plus 2 is just going to be 3/2. So y equals x over 2 plus 3/2, or x plus 3 over 2. All right, and that would be my equation in just our, a linear form. All right, we can take a look at the final equation, and that's exactly what they got, x over 2 plus 1/2. All right, and it's just a linear equation. This is just a simple linear equation. But you wouldn't have known that looking at the parameters. So we can actually do this. We can solve for the parameter t and then eliminate it by substituting into the other expression. So here are a couple problems for you to try on your own. Try to eliminate the parameter and then identify the graph of the parametric curve. Take, a couple minutes, pause your video, and see if you can eliminate the parameter. The first one should be straightforward, just like we did. The second one should also be straightforward. It's just we have cosine and sine, so you'll have to think about their inverse functions. Okay, welcome back. You should have had a chance to go through and attempt to work with these two different equations and try and eliminate the parameter. When we look at the solutions, all right, the first one we would have solved for, we would have taken our x equation, then we could plug in, right? We have y equals 3t and x equals t squared minus 2. We could say, t could be any real number. So we solve the second equation for t. We get t is equal to y over 3. So where we have t in our x equation, we plug in a y over 3. We end up with x equals y squared over 9 minus 2, which we can then just simplify and solve for y, and we can say y squared equals 9 times x, and it looks like this down below. It's a parabola, and it's kind of an inverse of the parabola of x squared equals 9 times y plus 2. So this is the graph that would be associated with that particular equation. In example 4, we wanted to eliminate the parameter using sine and cosine, and we can go ahead and take a look at what happens here when we go ahead and solve for these. We can say actually x squared plus y squared equals 4 cosine squared t plus 4 sine squared t. Factor out a 4, and we know that cosine squared plus sine squared is 1. So this is where your trig identities are huge. All right, you could have thought about using inverses and trying to substitute and everything else, or you could just go about it this way. And one of the reasons why you might want to do this is you could have plugged in the parametric equation into your graph to see what it looked like, and you would have said, oh, it's a circle, meaning we wanted x squared plus y squared. In which case, when you do that, you would find out it equals 4, which is just a circle with a radius of 2. All right, you wouldn't have known that looking at them, but had you graphed it on your calculator, you would have found that to be a viable option, which would have been a nice way to kind of get a jump start on this problem without going through and doing too much work. Now, what if I were to tell you that we have a line that goes through points A and B, and I want to determine a parametric equation for that line? This all of a sudden becomes a little bit different because now we're taking something that we know how to do linearly, and we're saying, well, how would we go about doing this with a parametric? All right. What do you think you might do? Where would you begin? Think about it for a second, and then we'll go over it. Well, the answer relies in vectors. So if we think about the point xy being an arbitrary point on the line AB, right? We have points A, point B, and we say P is just some arbitrary point on the line. Then we can take this figure on the right, and we can say that OP, the red arrow there, is going to be the tail-to-head vector sum of OA and AP. And that AP is just represented as some scalar times AB. Well, if we let that scalar be t, then we can write this out, that OP, vector OP is just vector OA plus AP, which is the same thing as saying OA plus the scalar times AB. Well, we know that the point xy, or the vector, xy, which is OP, right, is represented as vector negative 2, 3, plus the scalar times the other vector, which is just 3 minus a negative 2, comma 6 minus 3. And when we simplify that, all right, we simplify it down, we end up with this right here. Well, vector xy is negative 2 plus 5t, comma 3 plus 3t. Well, here are my equations. X goes to negative 2 plus 5t, and y goes to 3 plus 3t. By using vectors, we were able to create the equation of a line based on a parameter t. We use vectors to introduce that parameter, but it pans out. We can confirm our work by actually using those equations and seeing if that will give us those 2 points for point A and point B, and it does. Now, what if we only wanted to find the parametric equation for the line segment? We don't want the parameters range to go from negative infinity to infinity. Instead, we just want it to have endpoints at A is negative 2, 3, and B is 3, 6. Well, if we look back at the previous example, because that's where we got the equation of that particular line, we actually found that when t was equal to 0, it gave us point A, and when t was 1, it gave us point B. So the only thing we really need to do here is restrict our value of t to be from 0 to 1. If we restrict that parameter to those values, we pick up every point on the line segment between A and B. So we know the equation. We found the parametric equations for that particular line segment. We just need to know what are the values of t that will fill in that segment. And it's just everything between 0 and 1. Now, if you didn't know that right off the bat, we could say, well, I want to figure that out at, what is the x? We would want to find, well, if we plug in negative 2, 3 for x and y, what is our value for t? When we plug in 3, 6, what is our value for t? And that's how we would have found the range of values that we needed along that line segment. We can use parametrics to simulate horizontal motion. So say we have Gary walking along a horizontal line with the coordinate of his position in meters given by this particular equation right here, where s is negative 0.1 times t to the third minus 20t squared plus 110t minus 85, where t goes from 0 to 12. We can use parametric equations and our calculator, the graphing portion of our calculator, to simulate this motion. And we can use it to estimate times when he's changing direction. Now, if all we did is we plugged in the parametric equation, we would get this graph here where we see this line moving back and forth. It's not very helpful. Okay? So what we can do is we can actually do a couple different graphs, all right, where we say, x, the x value, x1, for our parameter is equal to this equation, and we say y1 equals 5. That kind of puts that line up there, and we can kind of trace it and see it goes back and forth as that time goes on. Then we can do another one where we say that the y value changes. We just make y equal, say, negative t. So it just kind of, the y is going down. So we can see it kind of starts and it goes to the left and goes down. And this way we can see the x position over time. And we can see that he changes values right here. He changes values again right here. And our y value kind of represents the time at which that occurred. So we can use our graphing calculator to find ways in which we can kind of trace that motion and simulate that motion. So in this lesson, we defined parametric equations. We learned how to interpret a parametric equation and how to eliminate a parameter. Additionally, we found parametric equations for lines and line segments, and we utilized our understanding of parametrics to solve motion problems. So you should now be able to graph a parametric equation, eliminate a parameter, and determine a parametric equation of a line or a line segment. You can also use parametrics to solve problems.